All right, so here you have spring and a mass. Hooke's law tells us that force is k times x, k is the spring constant. Newton's law is force is equal to mass times acceleration. When you combine them, you get this differential equation, which is second derivative of x is equal to minus some constant, in this case omega naught squared times x. That can be solved using methods of calculus for differential equations, and the solution is given by x equal to a times cosine omega naught t plus phi. Phi is the phase. All right, so how do we work this out using, say, Excel spreadsheet without having to know differential equations? What you do is you write velocity as rate of change of position, which you can then rewrite as difference in position here between two consecutive steps divided by time interval, label that as Vn. That can be simplified as this equation for updating position as a function of previous position and velocity times time interval. Likewise, the equation for the velocity, rate of change of velocity, this is mass times dv over dt equal to minus kx. You can write that as dv, change in the velocity over time, equal to minus omega naught squared times x. That can be turned into this equation for, it's basically a recipe for updating the velocities. All right, so here in the Excel spreadsheet, which I will make it available for you, what we do is you define variable k, spring constant, m for mass, omega is then equal to square root of k over m, in this case 1. You choose time interval small enough so that the approximation we made in this equation are not going to contribute a great deal of errors. All right, so then we basically start with a differential equation, turn it into difference equation, shown here as these two difference equations, and then you implement that in Excel spreadsheet. So you have a column for time steps, and then position at those times, velocity at those times. On the very top, you have initial condition, basically where at time t equal to 0, we are choosing position to be 1, so the amplitude is 1, and velocity to be 0. So you stretch the spring and release. And then you update the position values as well as velocity values using this recipe. All right, and then when you plot out the graph for velocity versus time, you see those sinusoidal graph as you expect. When you do the phase plot, which is velocity versus position graph, that will actually give you a circle. So basically what is happening is that the system is starting out at this point, and then it goes to this point and so on. So it goes around the circle in a clockwise fashion. That is the trajectory of the system. This is very important, not just for mechanical oscillations, but for electrical oscillations that we cover later in the course. All right, so one way to understand the phase plot is to compare that with what is done when people use complex variable to model oscillations. All right, so you have a complex plane. X-axis is the real axis, y-axis is the imaginary axis. So you write z equal to x plus iy, I being the square root of minus 1. So your point z is equal to x plus iy, where x is going to be cosine theta, y is going to be I times sine theta. So in this case, theta is going to change as omega times t. So as the time clicks away, the angle in the circle is going to change. And basically, you have this great relationship between Euler's constant, that is E, which is 2.71828, etc., raised to I theta can be written as cosine theta plus I sine theta. As a result, when you take the derivative of z with respect to time, you get I omega e raised to I omega t. Second derivative ends up giving you minus omega squared times z, which basically is the same kind of equation as this. All right. So what is done is you take real part of z, which then gives you x, which is cosine of theta, which is cosine of omega t, and that is what represents real oscillation.